Exciting and fascinating world of chemistry. We're looking at nuclear chemistry. Nuclear chemistry is a study of energy and reactions associated with the changes at the atomic level. Now, there's three other definitions you need to know for nuclear. First is radioactive. Substances that experience changes at atomic level are considered radioactive. So reactive is a substance. Reactivity is a tendency or process of substances that are radioactive. So the process itself is known as reactivity. Finally, decay, the process of change at atomic level, is called reactive decay. Now, we have some units of reactivity. The first unit is a gray. Gray is equal to 1 joule of energy absorbed per kilogram of tissue. We also know as a rad. A rad is 0.01 joules of energy absorbed per kilogram of tissue. Now, not all emissions affect the body the same way. So we came up with something called RBE, relative biological effect. One RBE is a beta emission, so it has a relatively low amount of emission effect, where gamma emissions have 10 RBEs. Gamma energy is expressed as follows. Now, particles themselves, they are either combined in bombardment or removed in an emitted or an emission to cause change in atomic level. Now, we have a couple different particles. The first is alpha. The way we originally symbolized it is the Greek letter alpha. And an alpha particle is 2 protons and 2 neutrons. Now, when we do something called transmutations, we need to express some of the reactions. The way that we do that is a helium nuclei, He4/2. Second, beta, which we talked about as far as the RBEs, Greek symbol for that, beta, B with a long tail. What do we have left? Just the electrons. So beta is electron. Since we don't have an atom that's pure electrons, it's E0/-1. We also have then gamma. This is the last particle originally identified. Gamma is pure energy. And it's from the binding energy. If we talked about before, binding energy is what holds a nucleus together. So when that breaks apart, the energy is gamma energy. All right, we also have some new ones that we recently found. We no longer worry about Greek letters because is what it is. All right, neutron. Neutron, neutrino, way we express a neutrino is N1/0. A proton we express as a nuclei of a hydrogen atom, 1/1. And then we have a positron. A positron is defined as the same mass as an electron, but then opposite charge. So it looks like an electron, but instead of being negative, it's positive. Now, we do have something called transmutations. Transmutations are defined as process of nuclear change in a reaction form. So, if we take a look at the first reaction, we call this an emission because particles are being released. So, this is equal. 7 minus 1 is 6. 14 added to 0 is 14. That equals up on both sides. This is known as, that. Look back at our chart, that's a beta. So this is called a beta emission since it's being released. Okay, the second type we can get through here is called a bombardment. Okay, in a bombardment, we're gaining particles. So in this case, we have 37 going to 36. What would we add to 37 to get 36? Again, it'd be -1. So it's going to be E0/-1. That, again, would be beta, but instead of being emission, it's called a beta bombardment. Okay, we'll do this transmutational series. One transmutation resulting in further reactions. We'll do this together in class. The last thing we'll look at today is reactive decay. Reactive decay is either one of two equations, either AT equals AO e to the minus KT, or ln of AT over AO is equal to minus KT. So that's how we find them out. We use the first equation if we're solving for either AT or AO. We'll use the second equation to solve for K and T. And these should look familiar because these are first order reactions we did when we talked about kinetics. Now, AT is amount of reactive isotope that remains. AO is amount of reactive isotope originally. E is a natural log base. T is time. And K is a reaction rate constant. And K is 0.693 over T1/2. All right, so let's look at a problem. Determine the amount of reactive material that remains after 2.500 years. If the half-life of the reactive isotope is 321.65 days, the amount of original reactive isotope is 123.8995 grams. Now, we're going to use this equation, and the reason we use this equation is AT is unknown. If we're solving for AT or AO, we use this equation. We use the other equation to solve for K or T. From the problem, we see that AO, the original amount of reactive substance, is 123.8995 grams. K, we said that K is equal to 0.693 over T1 half. Reactive half-life right here is 321.65. So we divide that through 5 sig figs, we get 0.00215545 per day. Now T is 2.500 years, but we see our days and years aren't the same, so we're going to convert this to days. And 365.25 days is 1 year. Cross them out, we get 913.1 days. Take our equation, put our values in. AT is equal to 123.8995 grams times E raised to the minus 0.00215545 per day times 913.1 days. My days cross out. I'm going to start with the log, so I'll multiply these first. Get an answer, take the E raised to that power answer, and then multiply by 123.8995 grams, and we get 17.33 grams. That's what we have. So look at the problem. We'll do this one in class. Calculate the half-life of reactive isotope if it takes 21.245 days to go from 19.567 grams to 13.788 grams. That's it. Take care. Be good. We're done.